Hi, welcome to MooMooMath. Today we are going to look at logs, and this is basically a log review. So if you're at the end of a unit and you want to learn everything in a nutshell about logs, you're in the right place. So we're going to look at the following items. We're going to look at how to rewrite a log from an exponential and an exponential back to a log. We're going to learn how to evaluate without a calculator. We're going to talk about the properties of logarithms, how to find inverses, and then how to solve equations. And again, this is an overview, so if you need specifics, you'll need to go to each separate video. Okay, so let's talk about rewriting logarithms. Okay, logs and exponential functions, this is an exponential and this is a log, they're inverses of each other. So what we want to do is we want to be able to take a log and write it as an exponential. So we have to start with the base. Well, the base on this log is b. So that's going to become the base of my exponential function. Then a log is always equal to an exponent. And in this case, d is my exponent. So I'm going to rewrite the d as the exponent to the base b. And what does that equal? That equals c. And that's what you're taking the log of. So that's how you rewrite from log base b of c is equal to d back to an exponential. So let's look at this exponential. We have an exponential and we want to write it in a log form. So you first start by writing log. Now remember the bases are the same, so this is also a base b. So I'm going to write my little b, it's a subscript, on the logarithm. And you take log base b of y is equal to x, and a log is always equal to an exponent. So this becomes your solution. You're solving for x. Okay, you're bringing down the x out of the power position. Okay, so now let's try another one. Wait, I'm going to try this. Sorry. If we wanted to do an inverse, we would have the 5 there, but I'm going to change that and just treat it as a basic exponential. So let's rewrite this one. So this is going to be log. And remember, our base is the same for exponentials and logs. So that's base 4 of y is equal to the exponent, which is x minus 2. Okay, and then this last one from log form, remember our base is the base of the log, so it's 3 to the x. Remember, a log is always equal to the exponent, is equal to 9. And as you can see, you can probably even solve that for x because we know 3 squared is 9, so x is 2. Okay, so now let's start evaluating. Okay, to evaluate without a calculator, you have to kind of understand logs. And if you're just learning them, you may want to rewrite into exponential form. So what I'm going to do is I'm going to take this log base 4 of 64 and set it equal to x. So I'm creating an equation out of an expression, but it's just there to help me solve it. Now I'm going to rewrite. So now I rewrite it as 4 to the x power is equal to 64. And 4 to what power is 64? Well, x is 3 because 4 cubed is 64. So I know that log base 4 of 64 is just 3, and that simplifies. So a good way to think of it is 4 to what power gives me 64. So let's take this next one. I'm going to erase this for you so you don't have as much stuff on here. Oh, whoops. Let's just clear the ink there. There we go. Okay, so let's rewrite this log base 16 of 2. So if I set this equal to x, I can rewrite this as 16 to the x power is equal to 2. Well, wow, I'm getting smaller here. So how do I take 16 to a power? What I'm going to do is I'm going to rewrite 16 so it has the same base. So 16 can be written as a base 2 if we take 2 and raise it to the 4th power. So 16 can be rewritten as 2 to the 4th, all to the x. So it's 2 to the 4x is equal to 2. Well, on this side, 2 is just to the first power, so I'm going to go ahead and write a 1 there. Well, once you have like bases, we know the exponents must be equal. So 4x equals 1, and so x must be 1/4. So in other words, the fourth root of 16 is 2, and that makes sense because 2 to the fourth power is 16. So the fourth root of 16 would then equal to 2. Okay, so anytime you have a root like that, you're actually getting smaller, therefore it's going to be a root. Okay, so let's look at the next one. We have a log base 1/3 is equal to 81. So let's rewrite this. Set this equal to x. And let's rewrite that as log, not as a log. Let's rewrite it as an exponential. 1/3 to the power of x, and I'm going to treat that as a full quantity, is equal to 81. Now, 1/3 is a little tricky, but I think I could write it with a base 3, because if I want the reciprocal of that, I just raise that to a -1. So that's 3 to the -1x, or negative x. That equals 81, but I can also rewrite 81 as a base 3. So 3 times 3 is 9, times 3 is 27, times 3 is 81. So that's 3 to the fourth power. So I have -1x is equal to 4, so x is -4. So that means I can simplify log base 1/3 of 81 just simply to 1, or what was our final answer? -4. Why -4? Negative means a reciprocal, so I would take 1/3 and find its reciprocal, and then I would raise it to the fourth power. So a negative exponent only means a reciprocal. That's all it means. It doesn't mean my term is negative. Sorry, I'm trying to clear the screen. There we go. Okay, so let's look at this next one. We have log base 3 of 1/9. Hopefully you get the hang of it. I set it equal to x. Then I take 3 to the x is equal to 1/9. Ask yourself, can I write like bases? In this case, we can. So 3 is already a good base, and I can rewrite 9, or 1/9, as 3 to the, second power, but it's the reciprocal, so it's the -2nd. So that means x is -2. So that means I simplify 3 log base 3 of 1/9. That's just equal to -2. It's the reciprocal, because 1/3, or a 3 to 1/9 would be a reciprocal. So it's negative, and then 3 squared is 9. Okay, now let's look at the last couple here. There we go. Now, on this one, if you have a base and a log with the same base, you are going to simplify it just to 3x. So when I have a base of 10 and a log base 10, because when we don't have a base on a log, it's just 10. It's assumed to be 10. So this will give you 3x. And that it's really that simple. It's just 3x. But I'm going to show you why that's true. So let's take log, or base 10 to the exponent of log of 3x. Now remember, this is an exponential form. Even though there's a log in the exponent, it's still an exponential form. I have a base, I have an exponent, and I'm going to set it equal to y, because I already have an x in the equation, so I don't want to set it for equal to x, because then that would get confusing. So now I'm going to solve for y. Now in order to do that, I need to take the log of, I need to change log form. So I'm going to change this to log form by taking log, and of course my base is 10 of y is equal to my exponent. Well, my exponent is the whole thing. It's that log of 3x. When we don't have a base, it's 10. So I'm just going to go ahead and write it in there so you can see it. Well, do you see? This is log base 10. That's log base 10 of y of 3x. So basically, y has to be 3x. So it just simplifies to 3, just the 3x. So anytime you have a base raised to the exponent, a log of the same base, whatever you have here, that ends up being the solution, what it simplifies to. Okay, so now let's look at this last one in this group. We're looking at log base 8 of 4. Okay, let's set it equal to x so we can rewrite it. So 8 to the x is equal to 4. Well, you got to stop and think, how can I rewrite 4 so it's to a power that would be 8? And there's not any value. I can't, because 4 to the first is 4, 4 to the second is 16. I never hit 8. But I can rewrite these both to a base 2. So I'm going to rewrite 8 as 2 cubed. Well, 2 cubed all to the x power is really just 2 to the 3x. And that's going to equal 2, and I can rewrite 4 as 2 squared. So now I've got my bases matching. Well, once my bases match, don't I know? Oh, the exponents have to be equal then. So I'm going to set 3x equal to 2. So x is equal to 2/3. And there's my answer. So you're always trying to get like bases. And that's how you simplify logarithms without a calculator. Okay, now let's talk about properties. Properties, there should be a lot of videos out there, a lot of information on condensing and expanding. Here's one example. Okay, the first thing you need to look at to condense logarithms, you need to make sure they all have the same base. So this is just a log, so I'm assuming the base is 10, the base is 10, the base is 10, and the base is 10. So now, anytime you have addition, you're going to have a product. Anytime you have subtraction, you're going to have a quotient. Anytime you have a coefficient to the log, it becomes an exponent on the term. So I'm going to pull these over. These coefficients are going to become exponents. So my first step of condensing is to move my coefficients. So this is going to be log base 3. This one didn't have a coefficient, so there wasn't anything to move, plus log base y to the 8th power minus log of x squared plus log of z to the exponent of 1/3. Well, we know 1/3 is really just a cube root, but we're going to leave it as a 1/3 for now. Now, all addition becomes products. All quotients or subtraction become quotients. So now I condense all 4 logs down to one single logarithm. So this is going to be a log base 10, and the fraction, anything positive is on top. So I'm going to have a 3 on top because that's a positive log. We don't write it, but there's a positive out there. Okay, y to the 8th. That's also positive. So that's also going to go on top as y to the 8th. Now I have a negative log x squared. Well, anytime I have a negative, it's going to go on the bottom of the fraction of the quotient here. And I'm going to have z to the 1/3. So I can write z all to the 1/3 power. I could also write it as a cube root, depending how it's presented. And that is how you condense logarithms. So what do you do first? Power rule, which is move the coefficients up, and then all addition is products, all subtraction is division, or you divide by that. And there's how you simplify that one. Okay, now let's look at doing the opposite. Let's expand the single log to multiple logs. So you have to think, well, how many logs am I going to have? You have to think how many terms I've got. I've got a 2, which is a constant. I have an x, I have a z, and I have a y. I have 4 different terms, so that means I'm going to have 4 logarithms. So I'm going to go ahead and separate and write 4 logs. So log, 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 and log. Now, my first step is just to separate those all 4. So log base 4 of 2. Now I'm multiplying times the x, so I'm going to add my second log, and that's log base 4 of x. Now I'm doing another product on top, so I'm going to do another addition, the square root of z. And now y is on the bottom, so I have to subtract log y to the 5th. Now I've separated it into 4 logs. Now from here, I do the last step, which is my power rule. So anything that has an exponent will move down. These 2 at the back both have exponents. X is just to the first power, so I don't need to worry about it. There is something special I have to do to log base 4 of 2, but I'll do that as my final simplify step. So let's go ahead and bring down log base 4 of 2 and my log base 4 of x. There is no power on those, so just bring them down. Now this fraction or this square root can also be written as a fraction z to the 1/2. So I'm going to bring down a 1/2 because that's the way to write a rational exponent for the square root of z. So that's going to become 1/2 log z minus, and then this exponent's easy, it's just a 5. So 5 log of y. Okay, right here you think you're done, but you're not. You're not done because this term right here can be simplified to a whole number. So 4 to what power is 2, and that's just 1/2 because the square root of 4 is 2. So that's going to simplify to a 1/2 plus log base 4 of x plus 1/2 log of z minus 5 log y. And that's how you would expand a logarithm. And that's how we do it. Oh, I forgot my base 4s here. I dropped those by accident along the way, so I'm going to go back and add those in everywhere I'm missing those. So don't be like me and drop your logs. Make sure your base follows you along. Okay, now let's talk inverses. Okay, for inverses, I'm going to type up a quick little list. The first thing you always do on an inverse is set your function notation. So if you have an f of x or g of x, replace it with a y. Okay, that's your first thing. So you just replace a y. Your second step, you're going to switch x and y. In your equation, you just switch positions because an inverse is switching your x and y coordinates. Okay, your third step is just simply solve for y. And that's our last step. So let's take those steps, starting with a log, and try to find the inverse. So our first step, we're going to replace f of x with y because that's what it is. So we're going to put y equals log base 4, and I'm not going to drop my base this time, of x minus 1 plus 5. Okay, now I'm going to switch the positions of x and y. So I'm going to put an x where the y is and write the whole thing out. And then I'm going to put a y where the x is. So this creates the inverse right there with the switch. Now let's just solve for y. So we need to get y by itself. So let's first isolate the log. So that means I'm going to move the 5. So that logarithm can be on the same side by itself. So it can be log base 4 of y minus 1. Okay, now I've isolated the logarithm. It's on that side by itself. Log of the base, log base 4 of some quantity. Now I have to do the rewrite. This is when you take it from log form to exponential form. So I have to think, okay, what's my base? Well, my base of my log is also the base of the exponent or exponential form. So it's base 4. The log always equals an exponent, so the exponent is x minus 5, and that's going to equal to y minus 1. So I'm really close to getting the y by itself. All I need to do is move the 1. So I'm going to take base of 4 to the x minus 5, and I'm going to add 1 to it. Now, I don't add 1 to that negative 5. That negative 5 is in the exponent. I just keep it as a constant at the back. And then to indicate that this is an inverse, I'm going to put a little y to the negative first on this side over here, and that indicates that is an inverse function. And there we go, and that's how you find the inverse. So notice we started with a logarithm, we switched x and y, isolated the log, and then we changed it to an exponential function. And that's how you find the inverse of a log. Its inverse is an exponential. Now let's do it the other way. Let's say we start with an exponential form. What do you think we're going to end with? You're right. We're going to end with a log. So let's replace g of x with y. That's just my output for my exponential function. And everything else stays the same. Just make sure we have an x and a y in the equation. Second step, switch x and y. So x replaces y, and then in the exponent, I'm going to put y minus 6. So that part's pretty easy. Replace f of x or g of x in this case, and then switch x and y. Now we have to solve for y. This is when it gets a little trickier. We want to isolate this base of 5. So what do we do first? We subtract 8. So we're going to have x minus 8, and that's minus 8 right there. You need to put that, is equal to 3 times the quantity, 5, to the y minus 6. Now, is the base isolated? And I hope you're saying no, it's not, because we have a coefficient of 3. So we need to divide both sides by 3. You could also multiply by 1/3. That may be a little cleaner here. So I'm just going to write it as 1/3 times x minus 8 is equal to, and then of course these 3's when we divide it, cancel. So 5 to the y minus 6, just so you can see another way to look at it. Okay, now I've got my base isolated. What's my next step to write the inverse? I have to get this y out of the exponent, and the only way to do that is to rewrite it as a log. So log base, well, the base is 5 of this quantity, which is 1/3 times x minus 8 is equal to the exponent, which is y minus 6. Okay, have I got the y by itself? Not quite yet, but I'm close, because all I need to do now is move the constant. So let's write log base 5, and we could distribute that 1/3 if we wanted to, but I think it's fine just the way it is. We've got 1/3 times the quantity, x minus 8, equal, then we've got to add 6 to get it away from the y, to get the y by itself. So plus 6 is equal to y. Now the y is finally by itself, and to indicate an inverse, I'm going to raise it to the negative first. So here is our final answer to rewriting an exponential as a log. So notice log base 5 came from the exponential function base 5 to some power, and those are inverses. Now let's try a couple solving problems. Okay, so let me see if I can move these out of the way for us. Okay, let's start with this first one. Okay, the first one is quite easy. This is just a simple log equation. Log base 2 of some quantity equals log base 2 of another quantity over here. Well, if we're taking the log of both quantities, that means those quantities must be equal. So I'm just going to rewrite this as log 3x plus 3 has to be the same value as 5x minus 15. And then if you solve for x, you're going to subtract 3 and get a 2x. You're going to add 15 to get your 18. So x must be 9. Now, this one actually is 9. But sometimes you're going to get a solution that doesn't work. Well, how do you check it? Well, you have to think a logarithm has a domain from some asymptote. So I'm just going to call it a sy. So some asymptote to infinity. If it's just a regular log without negatives or anything, it's just an asymptote to infinity. So its graph looks something like this, or the parent graph does. So we have some asymptote that the graph never crosses. So it doesn't have a full domain. So what we have to do is check and make sure when we plug in the value, in this case 9, that we aren't taking the log of a negative, because the log of a negative is undefined. So if we plug in 3 times 9, we get 27, and then we add 3. That gives us 30. So that means this would be log base 2 of 30. And that value is fine because we're taking the log of a positive. I'm going to check it on this side and see if we get the same thing. I'm going to take 5 times 9, which is 45. And 45 minus 15, that's also 30. So yes, both sides are equal. And yes, both sides work because we're getting a positive log. We're taking log base 2 of positive values. So our answer is just simply x is 9, and that does work, and it's not an extraneous solution. Okay, so now let's look at the second type of problem. We have a log base 3 of 4x plus 1 is equal to 4. We don't have logs on both sides to cancel out. So what do we have to do? We have to rewrite this from log to exponential. So what's our base? And our base is 3. So 3 to the 4th power, because remember a log is always equal to the exponent, is equal to 4x plus 1. Now we just need to isolate and solve for x. Well, 3 to the 4th power, 3 times 3 is 9, times 3 is 27, times 3 is 81. So I'm just going to simplify that. Then we're going to subtract 1. So that makes, what's that going to give us? 80 is equal to 4x. So x must be 20. Now, as with all good problems, let's check and make sure it gives us a positive log. So if we plug in 20 for x, that's 4 times 20, which is 80, plus 1 is 81. So guess what? That answer is absolutely fine. So indeed, our answer is 20, and that works well. Okay, so now let's try one that has 2 logs and a constant. Now, in this case, we have natural log. Natural log's base is e, and hopefully you've learned that. But what we're going to do is put together the rules and the properties. So we have 2 logs on this left side. What we want to do is condense it down to 1 logarithm. Well, in order to do that, we have to use the power rule first. So I need to move this coefficient of 2 up and square that 4, or square that 2 to 4. So I'm going to have natural log of 12x. I'm just going to bring that down. Then I'm going to have minus the natural log of 2, and with the power rule, I'm going to put the 2 there, is equal to 8. So first step. Now I want to condense to 1 log. So this is going to be natural log. I have subtraction. So I'm going to have a quotient. I'm going to have the 12x on top because it's positive, and I'm going to have the 2 squared, which is really just 4, on the bottom, is equal to 8. Well, that actually simplifies. This simplifies to natural log, and 12 divided by 4 is 3, so that's just going to be 3x is equal to 8. Now, I can't solve for x in the form that it's in, but I know I can rewrite as an exponential. So we need to think for a second. What is the base on a natural log? And the answer is e. We don't write it. It's like log. When you have a base 10, you don't write it, but there's an e. So I'm going to rewrite this as e to the 8th power is equal to 3x. Have I solved for x? No, but I'm very, very close. All I have to do here is divide by 3, which is also known as multiplying by 1/3. So my final answer is 1/3 e to the 8th power is equal to x. You can grab a calculator. You can take 1 divided by 3 times e to the 8th and get an actual value, or you could just leave it as this expression, which is the final answer. Okay, so that was log equations. That is the end of log equations. So let's take a quick look back at every topic we covered. Whoops. We started with first rewriting from exponential to log and log to exponential. Then we evaluated. Then we condensed and expanded with properties. Then we found inverses by switching x and y. And then we solved a couple simple equations. If you can perform all these operations with logs, you have a decent foundation on how to handle logarithms. I hope this video has been helpful.